Alright, so now we are ready to provide the proof of the pumping lemma, and then as a product of that proof, a mechanism for us to prove some languages to be non-regular. So how are we going to perform this proof? Okay, so to do this proof, basically we are going to use the idea that we said that if we have a language, if a string in a language that has more than p symbols in it, its length is greater than p or equal, then within the first p elements there's going to be a repeat state, and if that's the case, then if we choose that segment of the string that's between the two repeat states and repeating it, we are going to actually make a loop in our computation, but we won't change the outcome of the acceptance or rejection of our string. So we formally let the deterministic finite automaton that accepts the language M to be the formal definition of sigma q sigma delta q sub 1 and f, and as such we let a string s that's a member of A to be a set of a sequence of symbols s sub 1, s sub 2, s sub 3 to say s sub n, such that s sub I is a member of sigma. Okay, and we let as a result of this, let the length of S to be equal to n. Of course, if you have n elements in it, then the length of S is going to be equal to n, and we let the length of n to be greater than or equal to p, because we stated that the pumping lemma applies for the strings whose length is greater than or whose length is at least p, which means that we want n to be greater than or equal to p. If that is the case, then there is a sequence of r sub 1, r sub 2, r sub 3 to r sub n plus 1, such that r sub 0 is equal to q, or r sub 1 is equal to q sub 1, r sub n plus 1 belongs to the set of accept states, and this is such that, and that delta of r sub I and s sub I is equal to r sub I plus 1. This is basically what we said. It comes from the formal definition of computation of DFA. Okay, so what I'm suggesting here is that if M is a machine DFA that accepts the language, that recognizes the language L, basically what we have here is that the language of M is equal to A. Then if we pick a string S from A whose length is greater than P, so we have S sub 1, S sub 2, S sub 3, all the way to S sub n, so length is greater than or equal to P, then we can find a sequence of states that, each R sub I is a member of Q, right? And that the sequence of states starts from R sub 1, R sub 2, R sub 3, all the way to R sub n, and then since this language, this string S is accepted by our machine, the machine starts from R sub 1, which is the start state, goes through each of the sequences, so each of these sequences, so F sub 1 comes here, and then transitions us S sub 2 comes here, and then transitions as S sub 3 comes here, and then it transitions us, and S sub n, the last symbol, comes here, and then transitions us to the final state. And the last state is going to be one of the members of the accept states. And the transition function goes according to the delta transition on my machine. So R sub I with the symbol S sub I will take me to R sub I plus 1. So that's that. Now, notice that we know that I is between 1 to n for my strings here. So also, I know that n is greater than or equal to p. From here, I know that n plus 1 is greater than or equal to p plus 1, which is effectively, or rather, n plus 1 is that, which is effectively greater than p. Therefore, n plus 1 is greater than p. So from this, I know that there are at least p plus 1 states in R. Okay, so if you look at the R here, it has at least p plus 1. So I know that the length of R is going to be greater than p. I know that the length of Q is equal to p. And according to the pigeonhole principle, there exists an at least one repeated states in R. Okay, so I have at least one repeated state in R. Okay, so if I look at the first p plus 1 elements of my sequence, then 2 of them must be the same states. So let's basically visualize that. So basically, in the first p plus 1 elements in R, right, there is at least one repeat. Okay, so let's write this. So we have R sub 1, R sub 2, R sub 3, and we get to some R sub j. That is the repeat state. So this is the repeat state, the first repeat. And then this goes to some R sub L. And so this will be the second repeat. So basically so what I'm suggesting here is that let R sub j to be equal to R sub L to be equal to some Q sub R. We call it Q repeat. Okay, and I'm gonna go to R sub P plus 1 and go all the way to R sub N plus 1. So among the first p plus 1 states, I am going to have, so among the first p plus 1 states, I'm going to have at least one repeat state. So I'll pick the first one, R sub I, and the second one, R sub j, and the second one, R sub L. And so that makes, let's call this R sub p. sub v. Okay, and this makes my my sequence of states. So what's going to happen with each of these? So when S sub 1 comes in, R sub 1 goes to R sub 2. When I read S sub 2, from R sub 2 I go to R sub 3. When I read S sub 3, then I transition to R sub 4. And then when I read S sub j, then I transition from ij minus 1 to rj, and then when I see S sub j plus 1, I go to R sub j plus 1, and I go all the way to S sub l minus 1, which takes me from R sub l minus 1 to R sub l to R sub l, and then from R sub l with S sub l, I go to R sub l plus 1, and so on and so forth until I reach the end of my sequence. So S sub n will take me to R sub n plus 1. Okay, so here let's actually take a look at this R sub j. I'm going to basically signal this out. Okay, so that's that. And R sub l. So I'm going to also signal this portion out too. So from R sub j to R sub l. So these are the repeat states. Okay, and so what's going to happen is if I do this, then I can take the sequence that I have here from S sub j to S sub l minus 1, and also actually j plus 1 to l minus 1. And so, and also from S sub 1 to S sub j here. And so here I've got S sub l to S sub n. So these guys are my letters, my symbols. S sub 1 to S sub j, then S sub j plus 1 to S sub l minus 1, and S sub l to S sub n. Okay, so if I break my machine, my languages, affect my sequence of S sub 1 to S sub n effectively in this format, then I'm gonna go actually, sorry, I made a small mistake here. Let me just correct it before we go further. So this is going to be Sj minus 1, and this is going to be Sj. Okay, so this element from R sub j minus 1 to R sub j is Sj minus 1, and then from R sub j to R sub j plus 1 is Sj. Okay, then we are going to fix this piece also. Okay, so this is going to be Sj minus 1. This is going to be Sj. Okay, so from this combination, now let's do this. Let x be S sub 1, S sub 2 to S sub j minus 1. Y be S sub j, S sub j plus 1 to S sub l minus 1. And z to be S sub l, S sub l plus 1 to S sub n plus to S sub n. Okay, so let us break our string into x, y, and z. Okay, now let's take a look at the three conditions and see what's going to happen. First, let's take a look at J and L. Okay, since J and L, these two sequence of these two states that are repeat states are not equal, then since R sub j and R sub L are my repeat states, then R sub j basically is not the same as R sub L. Basically, this is the R sub j is the first of the repeat states, and R sub L is the second of the repeat state. According to this, j is not equal to L. Since j is not equal to L, then there exists at least one S sub I between R sub j and R sub L. From this, we realize that the length of y is going to be non-zero, because if you're in R sub I and then you want to go to some R sub L, there is at least one symbol that you need to read. So you need to read at least, let me actually write it a little bit more clearly here. You need to read at least one S sub k, one symbol. And since we need to read at least one symbol, there's at least one element that is in here, right? So R sub j plus 1, blah, blah. So therefore, the length of y will be non-zero. This satisfies condition number 2. So according to this, condition number 2 is met. Then let's take a look at the first p elements. Notice that we said that from here, we said that the length of R, the length of all these symbols, are greater than p, and among the first p of them, we have our repeat states. So since let me actually draw this. Then we say that since among the first p states in R, there is repeated states, and we know that L is less than or equal to p plus 1 from the fact that these first repeat states are among the first p states. Then we look at the size of x and y and realize that the size of x and y is less than L, which is less than or equal to p. So from this, condition number 3 is met. So this meets condition number 3. So the fact that our repeat states are among the first p elements, that means that if we put x and y together, which includes all of the symbols before the first repeat state and the second repeat state, their length is going to be at least, at most, p. Okay. Now, how about the most important condition? What happens if we pump our string? So since x, y, and z basically is s sub 1 to s sub j minus 1, s sub j to S sub L minus 1, and S sub L to S sub N, of which this part is X, this part is Y, and this part is Z. So we start from Q sub 1 to Q sub J minus 1. And then here, actually to Q sub J. Let me actually draw it this way. We start from Q sub 1 to Q sub J minus 1. And then from here we go from Q sub J minus 1 to Q sub J. And it takes us to Q sub L. Or rather, let's call these R sub 1, R sub J minus 1, R sub J, to R sub L. And then this piece takes me to R sub L plus 1. And this piece takes me to R sub N plus 1. And I know that these two states are repeat states. So this is, let's say, Q sub K and or Q sub rep to Q sub rep. So from this, I know that X takes me from R sub 1, from Q sub 1 to Q sub rep. Y takes me from Q sub rep back to Q sub rep. And Z takes me from Q sub rep to Q sub accept. Some Q sub accept just belongs to F. Okay. Now, if I take this first, the middle element here, Y, and I pump it up, then Y sub I takes me from Q sub rep to Q sub rep I times. Okay, so according to this, the delta of R sub 1 and X is going to be Q rep. Delta of R sub J and Y is going to go back to Q rep. And which means that the delta of R sub I and Y to the I is going to be also back to Q rep. And then from here, delta of R sub L and Z is going to belong to the accept state. So therefore, X, Y, I, Z is going to be a member of A. So if I pump the middle section of my string, or rather the section that belongs to the first repetitions of my repeated states, any number of times, I'm going to effectively not change the level of my computation or the process of my computation. So if the original string was accepted, then repeating the first portion of the repeat state is going to take me through the same process of the same sequence of states, which ends up being in an accept state. And so this completes my proof. All the three conditions. So this one, then condition number 1 is satisfied. So effectively, what I did is I satisfied all the three conditions: condition number 1, condition number 2, and condition number 3 of my pumping lemma. All the three conditions of the pumping lemma are met, and therefore, if S belongs to A, then S to the I, effectively the pumped version of S, is going to be also a member of my language, the set of strings, and therefore the pumping lemma is proven. So again, I'll just revisit this one more time. We start with assuming that there exists an deterministic finite automata that accepts the strings from A. Then we say let S be a string of the A that has at least length P. So at least length P. Then we say that there are a set of sequences that starts from Q sub 1, goes to one of the accept states according to the transition functions. Then we segment this into a bunch of sequences. So these are sub 1, R sub 2, R sub 3, R sub 4, and so on and so forth are the set of my sequences. Then we say that since the length of this sequence is greater than P, and we only have P elements in our automata, then at least 2 of those elements would be repeated. So in the first P elements that I have here, 2 of the states, these 2 states, will be repeat states. So I just single them out, and then I break my string into set of symbols before the first repeated state, set of symbols between the first and second repeated states, and then the set of symbols after the repeated states. When I do this, then I showed that the set of symbols between the 2 repeated states is going to be non-empty, because these 2 states, R sub j and R sub I, are 2 different states that are repeated, basically, or rather 2 different instances of the repeated states. Since there are 2 different, then there must be at least 1 element in there. So this will have at least 1 element or 1 symbol. Then I showed that these, and then also, since I assumed that there is, or effectively, according to the pigeonhole principle, the first repetition occurs between the first P states, the length of xy, or the length of the substring that contains the repetition, would be at most P. And then I showed that if I break this string into this combination of x, y, and z, since y, the portion of the string that's between the repeat states, take me from the same states through a route, loops back into the same state. If I repeat that any number of times, I'm going to start from a state, and then I'm going to loop through it a number of times, basically. So you go from q rep to q rep a bunch of times, and or I times, by taking y and pump it to the I. And if you do this, then your process of computation doesn't really change. The x goes from the start state to the first repeat state, then the y takes you from the repeat state back to the repeat state a number of times, and then z takes you from repeat states to the final state, which is one of the accept states. And therefore condition 1 meets, meaning that your pumped string is going to be a member of the language. And thus, the pumping lemma shows that all of strings in a regular language can be pumped, and that is their property. So if you have a language in which there exists a string that cannot be pumped, and its length is greater than P, then you prove that that language is not regular. So we're going to do this proof, or rather use this property, the pumping lemma, to prove some language is non-regular in the next video.